the talk. Okay, so I will talk about this Sherrington Kirkpatrick model, which comes from statistical physics. And so to introduce this model and to motivate this, I will start by looking at this problem called the dean's problem, where you imagine a dean at the university trying to divide, let's say, a dorm of students into two dorms by keeping friends as much as possible together and separating the enemies as much as possible. And the way you can look at this problem, so you consider this group of n people, and what the dean is given is this set of interaction parameters. So for each pair of people I and j, you have a number jij, which describes how much I and j like or dislike each other. Okay? Then we will divide this group of people into two groups simply by assigning everybody one of the two labels. So the groups will be +1 or -1. So the label tells you in which group you belong. And so this can be encoded by a vector of labels, right? And I will call it a configuration vector. Now, for each configuration, the cost function, which is called the comfort function, will be given by this sum over all pairs I and j of these interaction parameters multiplied by the labels. And of course, what this does is that if I and j are in the same group or they have the same label, you count those interaction parameters with the plus sign, right? If they're in the opposite groups, you count them with the minus sign. And so the dean's problem is to maximize this comfort function over all possible ways to split this group of people into two groups. Okay. So if you look at this, the objective there is pretty clear, because basically you want to keep, you want to keep the positive interactions as much as possible within the same group and separate or place as much as possible negative interactions in between groups. And we will be interested to understand the maximum of this comfort function, but not for any particular choice of parameters, but in a typical situation. Okay? So a typical situation will be modeled just by taking these parameters jij, and you take them as random variables. Okay? You generate them using random variables in a very symmetric way, actually. In this case, you just take them all to be independent for each pair, right? And you also take all of them from the same distribution. For example, we'll take it from the most convenient choice is the standard Gaussian distribution. There is a simple result which tells you that the behavior of the maximum actually does not depend on the distribution, as long, of course, it's important here that we choose it to be centered, that the average is 0. Let's say if it's a symmetric, if you just have plus or minus 1, then the probabilities that they like or dislike each other should be 1/2. Otherwise, it really changes the model. And the standard Gaussian is the most convenient one to work with. And so the question that we are interested in is, what can we say about this maximum of the comfort function, which is now a random number or a random variable because it depends on these random parameters jij, okay, asymptotically for systems of large size. So when the size of the system goes to infinity, how does this maximum behave? So when you look at this maximum of the comfort function, there are a couple of things which are relatively easy to understand. So the first thing which is relatively easy is just to understand the order of magnitude. Okay, so if you look what happens on average means, of course, on average over the choice of your random parameters jij, right? So the E represent expected value. So on average, the expected value of this maximum will be of order n to the 3/2. Okay. And also, if you look at this maximum on the right scale, if you divide it by n to the 3/2, there are some standard concentration inequalities which will tell you that this random number will be very close to the average, okay, with high probability. So if you want to understand a little bit more precisely than just order the magnitude, it's enough to look at the average rather than this random maximum. And so it turns out this question the physicists were interested in this question in 1970s, and in particular, Giorgio Parisi in 79 invented or discovered some exact formula, which I will show in a second. And from that formula, you can get the precise behavior for this maximum. So if you take this maximum of the comfort function, divide by its order of magnitude n to the 3/2, you get some exact limit, which is equal to 0.76 something. So just for fun, let's suppose that this limit is a good approximation for the case of 10,000. And what is interesting is to compare the optimal solution with the random solution. Now, the random solution means, the dean just divides everybody randomly in half, or maybe you just flip a coin to decide which group you go to. And from the point of view, of one person, if you are in that group, in this case, on average, you will end up with, 2,500 people you don't like, because your group will be about half the size, and half of them will be people you don't like, right? Now, under the optimal solution, you will have to deal with just 38 less enemies in your group. Okay. So whether it's worth it or not, that's another question. But the physicists explain this, heuristically by saying there are a lot of frustrated triples, because you can have a situation where you have two friends who are enemies of each other. So that's called frustrated triple. And what happens is that these frustrated triples can all be intertwined. So it really complicates this optimization problem, and your gain is very small. Okay. For example, a love triangle would be a frustrated triple, right? It's one example of a frustrated triple. All right. So of course the physicists were interested not because of the dean at the university, but because of this object called spin glasses, which are some magnets. Okay, it's some alloys of two metals like copper, magnesium, or gold iron with competing ferromagnetic and antiferromagnetic interactions. And experimentally, these spin glasses were discovered to have some interesting magnetic properties. So to try to understand this, first Edwards and Anderson in 75 introduced a model where the energy of the system, the Hamiltonian of the system, was given by exactly something like the comfort function that I described. So the only difference, of course, that when you talk about the system, energy of a physical system, it tends to be in the low energy state. So to match these two pictures, you have to put a minus sign. And otherwise, of course, interpretation of labels is just up and down spins. The interactions are ferromagnetic when the spins tend to align, and antiferromagnetic when they tend to anti-align. And in this original model, they place the spins on the lattice. Okay, so you consider, let's say, some big chunk of integer lattice in R3, for example, and only the neighbors on the lattice could interact. But because of this lattice condition, this really turned out to be a very difficult problem. Imagine this is like an Ising model, but with random parameters rather than with a constant parameter. So even now, even within physics, people are still not agreeing about how this model will behave, especially in the low dimension. And so to simplify this problem, Sherrington and Kirkpatrick introduced the mean field version of the model, where they just introduce additional symmetry by replacing this lattice by a complete graph. Okay? So now everybody can interact. There is no more geometry like the lattice. And of course, because you have a lot more interactions, it's conventional that you define an energy in a way that scales linearly. So the ground state or the maximum should scale linearly with the size. So that n to the 3½ that I mentioned, you take 1 square root and make this a part of the definition, right, to make sure that now this is of order n. And so to summarize, this will be our object of interest, this Hamiltonian. Now, I'm not going to write a minus sign like in physics. I will keep writing plus sign. And even though I will call it energy or Hamiltonian, I will really talk about the maximum, trying to maximize this random function, which is a function on these vectors of configurations with parameters, random parameters, which are independent standard Gaussian. And so our motivation is to compute the limit of the maximum scaled by its order, which is now n. So what the physicists were actually doing, or what they always do in this situation, because maximum or minimum, it's not a very nice functional of your function. So what you do instead is look at this quantity called the free energy, which is, you can think of it as a nice or smooth approximation of the maximum, where you introduce this parameter beta called inverse temperature parameter. And instead of looking at just one configuration which maximizes your energy, you now sum contributions from all configurations, and the contributions from sigma is given by that exponential beta h. Then you take a log and divide by n beta, and this is your free energy. And turns out there is a very simple relation between the free energy and the maximum, okay? That the difference between the two is at most log of 2 over beta. So when temperature goes to 0 or beta goes to infinity, this free energy is essentially your maximum scaled by n. Now, you can see these inequalities very easily, right? Because for the lower bound, you just keep one term in the sum, right? Instead of looking at the sum, you just keep one largest term. So log and exponent cancel, betas cancel, and you get exactly maximum over n. For the upper bound, you replace every term by the largest one, right? And you have 2 to the n configurations. So that 2 to the n, that's what gives you the additional log of 2 over beta. Also, because the difference does not depend on n, and it's small if you fix your beta, this allows you to interchange the limits. If you like, or in fact, that's how we do things, that first you compute the limit of the free energy for any fixed beta, and then you take limit of beta goes to infinity after that. Okay. So that's exactly what Parisi discovered. Is not the formula directly for the maximum, but the formula for the limit of the free energy. So let me show how the formula look like. So the limit for the free energy is given by this variational formula where you minimize over some parameter zeta. And as you can already see from the last term, zeta will be a function on 0, 1. Okay, you will minimize over functions on 0, 1. And not just any functions, but these types of functions which are just discrete cumulative distribution functions. So in other words, these are just step functions with finitely many steps, increasing from 0 to 1 on the interval 0, 1, which encodes clearly it encodes some kind of distribution. And this middle term is more complicated. So you have one linear term, and the middle term is nonlinear functional of zeta. And it can be written like a function at times at 0, 0, where this function ftx is a function of time on 0, 1, and spatial variable on the real line. And this is a solution of this parabolic differential equation with the boundary condition at 1 given by log of hyperbolic cosine beta x. So what you do is you solve it backwards from 1 to 0. Of course, your solution depends on zeta because of this factor in front of the nonlinear term. And then whatever you get at time 0, you just call it a functional of zeta. Now, the truth is this is just a convenient way to write something explicit, okay? Because if you, on each interval where zeta is constant, if you make this change of variables, e to the zeta f, this new function phi satisfies exactly this classical heat equation. So you can write the solution explicitly on each interval, on each step, right? So the only thing you need to do is just make, a different change of variable every time you go to a new step. And at the end, at 0, your solution will be an explicit formula, just some explicit recursive formula in terms of these zetas. And in fact, the way it's computed in physics or in mathematics, you really arrive to this explicit formula first. There's a differential equation is just a convenient way to write it after that. Now, this parameter zeta is called the functional autoparameter. Okay, in physics, when you say something is an autoparameter, it means that that thing completely encodes all the properties of your model that you are interested in. And we'll see that slowly that's exactly what happens. And let me mention right away that this was rigorously first proved by Talleyrand in 2003, and then I gave a different proof in 2011, which is, it was well known that, everybody knew how to write this proof, except for one obstacle that was left. Since I solved that obstacle, I write up the proof. Okay. So, since I will talk in these two talks about the Sherrington Kirkpatrick model, I want to mention that, this solution that Parisi discovered, it was, after that, physicists apply this to many, many other problems of different kinds of problems, including this type of problems of kind of random combinatorial optimization problems. So just to show a couple more examples of these success stories, let me mention minimum matching and traveling salesman problem. So both of these will be in the same setting of what is called mean field random distance model, okay, where you start with a complete graph. And now the interactions, so on each edge, you will put a random number, okay, which will have the meaning of the distance between the points. But it's not really the distance. It's just a model of the distance using random variables. Okay? And this model is said to have pseudo-dimension d if the density scales at 0, like x to the d minus 1. Right? And the reason for this is very simple, because it just mimics how the distance would behave in dimension d if you sample points, let's say, in the neighborhood of the origin. The chance that you will be within distance x is proportional to the volume, right? Which is like x to the d, and the density is just derivative of that. So this mimics what would happen in dimension d. Okay. So the minimum matching is the following. You look for perfect matchings. Perfect matchings is just you choose. First of all, this will only work in the case when n is even. And when n is even, you look for the set of edges with each vertex incident to exactly one of these edges, right? Which just means you divide everybody in into equal groups, and you match 1 with 1. And you want to do this in optimal way, in the sense that the total length of these matchings will be as small as possible. And so the physicists discovered that when you look at the length of this minimum matching, it will scale like n to the 1 minus 1 over d, and it's given by some explicit formula in terms of some function g, which is a solution of some integral equation. Now, in most cases, you have to do this numerically, but in pseudo-dimension 1, you can really solve this by hand, and you get, first of all, in dimension 1, there is no scaling, right? Because when d is equal to 1, you don't need to scale. It really tells you that no matter how big the size of the system is, the total matching will be very short, of order 1. And you get pi squared over 2, okay? And this was proved mathematically by Aldous in the case d equals to 1, and in the general case by Vaslund in 2012. Now, traveling salesman, in the same setting now, you look for Hamiltonian cycles, which is just a closed walk that visits every vertex once and comes back to where it started. And again, you look for the shortest closed walk like that. And you get something very similar. You have the same scaling for this length. And you get some explicit formula in terms of some solution of some integral equation. And here, even in d equals to 1, you have to solve this numerically, but you get something like this, 2.04. And this case was also solved by Vaslund in 2010. Okay. All right, so these are just a couple of more examples. Let me go back to the Sherrington Kirkpatrick model and say that before Parisi, the physicists already had some heuristic, non-rigorous method to compute this, which is called the replica method. Okay. For example, the Sherrington and Kirkpatrick, in their original paper, they already had a formula, explicit formula for the free energy, but they knew that it's not correct at low temperature, which is the interesting region. So what people were trying to do after that is to what is called break replica symmetry in the correct way, which really meant that in this explicit computation, there is some set of parameters which emerges naturally in this computation. Sherrington and Kirkpatrick chose them all to be equal. That's called replica symmetry. And so it looked kind of like a weakest point of this argument. So people were trying to look at different choices, but they all failed. Okay, they were getting the same wrong result until Parisi looked at this and he introduced really a new fundamental principle in this heuristic computation, which is, of course, will be very heuristic also. But once you see it, you should really feel like this is completely obvious. If you saw it, you would probably do the same thing. So what he said is that when you maximize a function which depends on a negative number of variables, you should really minimize. Okay. That's the fundamental principle. Okay. Now notice that it doesn't work the other way around. If you minimize a function, you cannot go back and maximize. So that only works in one direction. But there is something really to this, because it always works beautifully in physics. Every time you have a problem where, sometimes there are several sets of parameters, if you have negative number of variables, you just minimize, and that works. So there's something still to understand here. It means that that computation was rather non-rigorous. Okay, that's what it means. Okay. But it worked, and that's the only thing that counts in physics. And so this allowed him to, it was not the end of the story, but it really put him on the right track. And with a lot more work, he was able to find the correct solution, okay, which gave the correct answer that people already knew numerically. And over the next 5 years after he discovered this, his solution was interpreted, was interpreted in terms of some meaningful physical properties of the system. So his solution, it was, as I said, it was just some explicit computation where these parameters, they don't really have any explicit meaning, but you solve it, And then people really wanted to understand what does it mean. And over 5 years, they really figured out what it really means. But I want to emphasize that no explanation of where this is coming from was given after this interpretation. Simply, now you have clearly defined picture, which I will describe in the rest of this talk. But it was up to mathematicians to try to figure out where this is coming from, okay, or how to explain this. So more precisely, the Parisi solution was interpreted in terms of properties of the Gibbs distribution of the system, okay, where the Gibbs distribution is a probability distribution on the space of configurations, where you assign your configuration sigma a weight proportional to that exponent beta h, which we have already seen. And so for this to be a probability distribution, you have to divide by the sum, right, which is called the partition function. So in statistical physics, this distribution represents the probability to observe your system at a given temperature in this particular configuration. So it has a very important physical meaning. So if you can say something interesting about it, it really does not require any more motivation. But if you also think from point of view of our motivation, we can see that the Gibbs distribution is really just a relative contribution of this particular configuration sigma to the sum, right? Since we are trying to understand what this free energy looks like, well, if you look at that sum, the Gibbs weight is simply relative to other sigmas. What is the contribution of this one sigma? So at least, at a very intuitive level, if you can understand the Gibbs distribution or discover some special structure in the Gibbs distribution, this should be helpful in the computation of this free energy.
Is this text at the very bottom? Should be beta?
Oh yeah, it should be beta, yeah, sorry. Yeah. So, and the reason why it should be helpful, you can imagine that if you look at all your configurations, and suppose you can discard a large part of your space of configurations which really do not contribute, which are very unlikely, and you keep only the likely configurations which contribute to the sum. And then you discover that that set of likely configuration has some very, very special structure. That means it should really help you because you're really now looking at some sum over a much nicer set, and maybe you get additional information. And so that's exactly how things work, both in physics and in mathematics. Okay. So this Parisi solution, what it really describes is some special structures of the Gibbs distribution. And so the basic question that we will think about is, how does the set of the likely configuration look like? Okay, or does this set of likely configuration have some special structure? Now, the first thing to note is that you cannot really look at individual configurations because even the most likely configuration is exponentially unlikely because your system is of exponential size. So you cannot look for specific finite set of configuration which will carry some weight. So what you should think about is you should relax this and say, maybe I will find clusters of configurations which carry most of the weight. And I will find structure in those clusters. So what you see, so here, if you look at your energy landscape, right, on this configuration space, you know that the most likely outcomes are near the peaks. Right? Those are the most likely ones. You know they, by themselves, are really unlikely to be observed. But possibly, if you go a little bit below the level of the peaks and consider some clusters, around the peaks, hopefully you can pick up enough weight that all the weight will be accumulated on these clusters, and they are still small relative to the whole system that you see some special structure. Right? So that's one way to think about this. Now, you don't approach this actually directly because you are in high dimensional space. you have this random function that you really don't understand how it looks like. And what you do instead, so it turns out it's a good idea to look or first study the geometry of the Gibbs sample. So in some sense, it really means you let the Gibbs distribution reveal itself. You just take your Gibbs distribution, and here, let me first remind that we have this model with random parameters. Then we define the Gibbs distribution, which is random, right, because it depends on these random parameters. And then you sample, a lot of points. So these are not necessarily the most likely points, but since you observe them, you hope that most of them are representatives of these nice clusters. And you try to look for structure in the sample, in the Gibbs sample, okay? Now, of course, all the statements will become precise only in the limit when the size of the system goes to infinity. So you're really looking at the sequence of models. And you have to, if you want to see some structure, you have to look at them all on the same scale, right? So that's why here, your configurations on systems of size n, they have length square root of n. We will always scale them to look at this whole system on, let's say, the sphere of radius 1. As n increases, what you hope is that you will start seeing some special structure asymptotically. And so what Parisi solution predicts that we will see something more than clustering, something much better than clustering. But also because this is a random, you see that you have kind of two levels of randomness. You have random model, and then you sample from a random distribution. So this is, of course, a random picture. All the distances between these points are random. And part of the Parisi solution tells you also that you will see a very special pattern of randomness. That if you tell me, if you look at the distance between 2 points, and you tell me what is the distribution of just this one distance, it turns out then I can generate this picture for you just with this one piece of information. I can forget about the model, the Gibbs distribution, and just knowing how one distance behaves will describe how all the distances behave, which they are very correlated, but this one piece of information will be enough. And again, I'm emphasizing this will be only, you can say it with epsilon and deltas here for large system size, but it will become exact statement in the limit. So let me quickly formally write down what I just said. So we consider a sample from the Gibbs distribution. We scale them by square root of n. Now, instead of distances, we will actually record the scalar products between them, which are called overlaps by the physicists. Of course, in this case, the scalar products encode the same information as the distances. And so this Gram matrix of overlaps encodes the geometry of the sample. And what I said is that the Parisi solution can now be described in terms of the properties of this random matrix. However, what we will do is first pass to the limit to talk, to give precise statements instead of worrying about epsilon and deltas. Okay. Now, passing to the limit means that this really means that when you look at that picture that I described, that its statistical properties stabilize when you increase the system size. So in other words, the distribution of this matrix converges to something. And so that limit will be denoted by a matrix R. Okay, that's an infinite Gram matrix in the limit. Now, the truth is we don't know how to prove convergence like this in most cases, but this is a very minor point. It's enough to look at subsequential limits, show that the Parisi picture is true for any limit, and then you get all the information you need. So for the purpose of these talks, I will just assume that this whole sequence converges in distribution. Okay. And so now I can describe the Parisi solution precisely without epsilon and deltas in terms of this limiting matrix R. But this description, it will not be very illuminating, okay? It will be a little bit, it won't look so interesting. And to make it really interesting, we'll go one step further and give another representation for the limit. And this can be done very easily by this beautiful result that I will show now. It will be a consequence of this fact that in the limit, you inherit two very basic properties from your model. Of course, first of all, this will be non-negative definite matrix. And then it will have this symmetry. This is called exchangeability, that if you permute rows and columns by the same permutation, you should get the same matrix in distribution. Now, for the original matrix, this is completely trivial property because what is this permutation? It's just sorting or renaming the sample, right? And then in the limit, you get it just by the definition of the limit. Now, for any matrix with these two properties, a Dober-Sudakov representation tells you that there exists a random measure G on a separable Hilbert space H such that this matrix that you're looking at is in distribution nothing but the matrix, the Gram matrix of scalar products, a gain of IID sample from this measure. Okay, I will call this asymptotic Gibbs distribution. So in other words, before you passed to the limit, you had a Gibbs distribution, you sampled points from it, and you were looking at scalar products. You were on some high dimensional space, and as dimension goes to infinity, you just end up on a Hilbert space. In the limit, you still have a random probability measure. You're still sampling, So you end up, that picture that I showed before, it's just, we are now in the limit. Your Gibbs distribution is now on a Hilbert space. It's still random, okay? You can think that this randomness is sort of inherited from the sequence of models. And then you are sampling points. There is no more scaling because, we always scale in such a way that in the limit, we are just looking at scalar products. And so the Parisi picture will be described in terms of this Gibbs, asymptotic Gibbs distribution. You can say it in terms of overlaps, but really it will mean, because now these are precise statements without epsilon and deltas, it will really mean you're saying something specific about the Gibbs distribution. And so this property now will be exact here, that if you tell me the distribution of one overlap without any epsilons, I will generate you this picture exactly just by this one piece of information. So summary of the Parisi solution, the first one, it's exactly what I just said, that you give me the distribution of one overlap. I denoted zeta because it will be essentially the same zeta as in the Parisi formula. Right? This is just describes probabilities that your 2 points belong to a set. And this is the functional autoparameter because once you know zeta, you can determine the joint distribution of all overlaps exactly. And in particular, you can also determine the limit of the free energy by this Parisi formula. So that zeta, which appeared in the Parisi formula, is just it has this physical meaning of the distribution of one scalar product. Okay. Now, I promised you something better than clustering. Something better than clustering is called ultrametricity. And ultrametricity just means that if you look at any 3 points in the support of your random measure, they will satisfy strong triangle inequality, okay, ultrametric inequality. In other words, the support of your measure is an ultrametric subset of the Hilbert space. Now, why this is better than clustering? Because I call it ultra clustering because it really gives you clustering at every distance. Okay, because if you pick any distance d, and now define a relation between points by this condition that they are within distance d from each other. This condition is an equivalence relation on the support because of this ultrametric inequality, right? If 2 distances are less than d, automatically the third distance is less than d. So at every distance, your support will break into equivalence clusters. which have diameter at most d, but separated by a distance bigger than d. That's exactly like clustering, except you have it for every distance. Okay, so as you can imagine, if you start with small clusters and you increase the distance, your small clusters will just merge into bigger clusters, right? And then merge into bigger clusters until at large distances, you just cover the whole support. So you can visualize this by this clustering process, but what I'm going to do is I'm going to discretize things a little bit. I'm going to record this clustering at finitely many distances so that this clustering picture will look very regular. Right? And then what you will see is what I just described, that at a small distance, you'll just have a lot of small clusters. Right? When you increase the distance, some small clusters merge into a bigger cluster. So at the second level, you have, again, equivalence clusters, but of a bigger diameter, right? And you continue this, you have this clustering process until you end up with one big cluster. And what this tree encodes is the geometric information about the support of the Gibbs distribution, because it tells you, now if you pick two clusters here, pick 2 points in these clusters, you can tell me what the distance between the points is, because you just have to find where they merged. Now, it will not be exactly that distance, because they could have merged a little bit earlier, right? Because I'm recording that they merged only at that moment of time, but it's possible that they merged somewhere right before that. But this distance will be in between this one and the previous. So if you discretize well enough, you know all the distances between points up to a little error in your discretization. Now, another property of the Parisi solution tells you that this is not just any ultrametric tree. This tree is infinitary, which means that every vertex will have infinitely many children, which means that anytime your cluster breaks into subclusters, it breaks into infinitely many subclusters. Okay? So this will be infinitary tree, and this will be important later. And so the question is, okay, why did I discretize? Because if you go back here, I could have just as easily drawn, those merge points at any point of time. Well, the reason is that on one hand, we don't lose any geometric information about the distances between points except for this little error, right? But what we gain by discretizing is we gain very explicit description of the randomness, because this is a random measure. You want to describe not just how it looks geometrically, but what are the probabilities. And so there will be a probabilistic property which will say something like this, that okay, if you denote the cluster indexed by any vertex alpha in your tree by H alpha, so H alpha is a subset of your Hilbert space, or a subset of the support, you want to know what their Gibbs weights are. And if you look at the Gibbs weights of all these clusters, there is a procedure, very explicit procedure, which I will show in the second talk, which tells you exactly how you can generate all these weights of clusters very, very explicitly by what is called Royal probability cascades. And so this is also something that the physicists discovered. They discovered all these statistical properties, but Royal was the one who realized that, there is this very explicit, simple construction behind what they are writing. That's why it's called Royal.
Just the sum, is the Gibbs weight of a cluster the sum of the weights of the?
Well, the cluster is really a set. So it's just a measure of that set. So so the cluster itself, it may be non-discrete, right? You can. Yeah, the weight. Okay, so, and in particular, such explicit description allows you all kinds of explicit computation, and that's one of the reasons the free energy, you have this explicit formula for the free energy, because you just use explicit computation because you know exactly how your Gibbs distribution looks like asymptotically. So let me do a quick overview of my second talk, what I will talk about. So all of this is a Parisi solution. Now we can prove all of these statements. And the mathematical results, they start with this paper of Guerlain de Guerra, where they discovered some identities on the distribution of the overlap. So I'll show them also in the second talk. And when they discovered them, people realized very quickly that if you combine them with ultrametricity, you completely reconstruct this whole picture. You know that that's exactly the measure you're looking at, given by the randomness is given by the Royal probability cascades. And this Guerlain de Guerra identity is a probabilistic property. It's really a property about distribution of the distances. So what you might think is that these identities is just another way to encode the randomness of your Gibbs distribution. Okay? So you have, and really that's what people thought for a long time, that you have two complementary properties. You have a geometric property of ultrametricity, and you have some probabilistic properties given by these identities. Together they complement each other and really describe the whole picture. So my main contribution to this field was to show that these identities in fact imply ultrametricity. So once you have these identities, which are rigorous, so that's a mathematical result there, ultrametricity is just a consequence. So this geometric part of the Parisi solution, it's really explained by these probabilistic properties also. Okay. So in this sense, almost everything is explained by the Guerlain de Guerra identities. Okay, so that's the point, that almost everything is explained by these identities. So in the second talk, I will show all of these things, Royal probability cascades, Guerlain de Guerra identities, and where they are coming from, and also to give some idea about some ideas in the proof of this statement, that how you get ultrametricity from the Guerlain de Guerra identities. Okay, I'll stop here.